Hi, we are back with filling in some of the details of the RSA encryption algorithm. So I'm just going to write down where we're at and what we've done, and then we'll see what we're going to handle in this, what will hopefully be a shorter than typical video. So we're with the RSA encryption algorithm. We have n is equal to p times q, where p and q are primes. And then we have computed phi of n, which is p minus 1 times q minus 1. And then we have chosen b such that the GCD of b and phi of n is 1. That means that b is invertible. And then we compute a such that AB is congruent to 1 mod phi of n. Then that allows us to determine the two functions that we need. The encryption function looks like this. You take x to the b mod n, and then when you wish to decrypt, you take y to the a mod n. So the public key is B and N, and the private key, really all you need is the A, but the private key is A, and A is basically obtainable once you have P and Q. So that is the public and the private parts of the key, and that is how the plain text X is encrypted, and then the DKY is how you decrypt the ciphertext. Okay, we just had a discussion where we showed that x to the b to the a is indeed equal to x mod n, and we did that in two cases. We did that in the case where x is in Z and star, that's the invertible elements mod n, and we also did it when x is in Z not invertible element. Okay, so we've handled that detail. We are now assured that should we use this encryption and decryption function, that if we encrypt something and then we decrypt it, we indeed get back exactly in every case to what we started with. Also coming up when we devised our own encryption systems was a couple of things that were noted. One is cracking or so let me just put it this way, cracking RSA is basically equals factoring n. If you can factor n into P and Q, then you can get the key and the security is finished. So clearly the security is resting on the fact that you cannot factor n. Okay, that's one thing. The second thing we noticed when we were doing our small examples to see how this worked, the second thing we noticed was that doing this calculation, x to the, let me just, in fact, well, I'm just going to see which letter I want to use so I stay consistent here. So we have, if we're trying to make a calculation like this, x to the c mod n. So this is a modular exponentiation. If we want to make this calculation, if we go ahead and do this without much thought, then it is incredibly slow. And you've found out even when you were doing a small system that your calculator can't handle that very well. And you can imagine when the numbers are much larger as they are in a commercial system, that this calculation could be prohibitively long. So what we're going to do today in this video is look at the algorithm that we're going to use to do modular exponentiation so that we can make these calculations here efficiently. So this is not about the accuracy of the calculation or whether the calculation is the correct calculation. It's about how can we quickly calculate something that maybe would look like this: 4396 to the 2374 mod 11,475, something like this. Okay, so if we have that kind of a computation, how do we do that with relative speed? So the way we're going to do that is using the square and multiply algorithm. This is sometimes also called binary powering. Okay, so it basically reduces the number of modular multiplications that are required. So that is the idea. We have the square. Let me just take off the keyboard. Ignore that little 5 there. The square and multiply algorithm. Okay, so we saw a nice presentation from Jeffrey today about computational complexity. So what we want to do is reduce the computational complexity of this calculation, and this will allow us to give since RSA is basically two of these calculations, one for encrypting and one for decrypting, that just gives us the computational complexity of the RSA encryption and decryption functions. Okay, so let me just in fact give you the result before I show you how the algorithm works. We have x to the c mod n. We're wondering how many computations will that take, and let us let L be equal to the number of bits in C, and let K equal the number of bits in X. Okay, so we saw on the previous lecture about computational complexity of some basic algorithms. If we were to multiply X times X, that calculation that has of complexity of order k squared. Okay, and then what we're going to see is we can reduce the number of multiplications required. So our idea here is with the square and multiply algorithm is to reduce the number of modular multiplications to at most 2L. Okay, so each one we do is going to be k squared, and we're going to reduce it down to 2L. That is going to give us the result that modular exponentiation will have cost O times L of k squared, and n is an upper bound, so n is greater than L and n is greater than k. So that means that the RSA encryption cost is of order log n cubed. Okay, because we calculate k. We calculate k as the log to the base 2 of x, and we calculate L as the log to the base 2 of c. Okay, we saw that in the previous lecture. Okay, so we now have, with this square and multiply algorithm that we're going to see, we have a computational cost for RSA encryption. Okay, so let's see how this algorithm works. We are going to, this is our thing that we're trying to do. We are going to take C and represent it in binary. So represent C in binary. And then that means C will look like this. C will be the sum from I equals 0 to L minus 1 of CI 2 to the I. Okay, so that is just a shorthand notation for representing C there in its binary notation. And of course, in binary, these CIs will be 0 or 1. So I'm going to first write out the algorithm, and then we'll go through with a small example so we can see what's happening. Then we'll go through with actually a slightly bigger example. Okay, so here it is. I'm going to call it square and multiply. Then there's going to be 3 inputs, x, c, and n. Okay, so I'm going to take a variable z, which I am initially going to set to 1. So z is initialized to 1. And then for I is L minus 1, starting at L minus 1 down to 0. So what is L? L is the number of binary bits in C. So we're going to do the following. Here's what we're going to do. We're going to say Z is going to be set to be Z squared mod n. And then if Ci is equal to 1, then Z will be Z times X mod n. Okay. That is the algorithm. Return Z. Okay, the square and multiply algorithm. I will almost undoubtedly ask for you to operate this algorithm on the final exam to do a modular exponentiation. Okay, let's take an example so we can get a feel for what's going on. Example. My example is going to be 5 to the 6, and I'm going to say mod, and I'm just going to say here big N. Like bigger than 5 to the 6, so I never have to worry about actually doing the modding anything out as I'm going through. Okay, we'll do another example where that's not necessarily the case, but this one I think we'll do it this way just so that we can see what's going on. So I mean, just think of n could be like, I don't know, it doesn't matter, 10,000 or something like that. It's just some big number so that we can just work in the equivalence class without actually ever having to reduce mod n while we're running through this algorithm. Okay, so the way that what we need to do is represent C. C is 6, and we're going to represent C in base 2. So that will look like this: 1, 1, 0. That's in base 2. That means L is equal to 3 because there's 3 binary digits there in C, and the number that our base here is 5. Okay. So now what happens when we go through this algorithm? Z gets set equal to 1 at the beginning, and then I will be starting at 2, and it will be going down to 0. Okay, so we're going to go through each one of the steps. So the first step would be when I is equal to 2. And so what would happen then? Well, Z is set equal to Z squared. So that means Z will be equal to Z squared, and Z is currently 1. So it'll be 1 squared, and that'll be 1. And then we will check whether C2, because I is 2, we check whether what is the value of C2. And so this is right there is C0, right there is C1, and right there is C2. So I'm going to take a look at C2 because I is 2 here. So I'm taking a look at C2. C2 is equal to 1. So therefore I take Z and I put Z equal to Z times X, and X is 5, and then that calculation is 5. Okay. Then I is decremented and I gets down to 1, and then Z is equal to Z squared. Z is currently sitting at 5, so Z becomes equal to 5 squared, which is 25. Then I take a look at what is C1. C1 is 1, so Z becomes equal to X times Z, which is X is 5 times Z, which is currently 5 squared. Well, actually, let me not write it that way. Let me write it this way, 25. And so that becomes equal to 125. That's when, because C1 is equal to 1. I is decremented again, and I get that Z is equal to Z squared. That's 125 squared, and I could work out what that is. I don't have that number written down, but clearly that's some number, Z squared. Okay, and that is, we can do anything. This next step, we don't do anything because C0 is equal to 0. Then we stop, and then we say, therefore, 5 to the 6th is equal to 125 squared, that number. Okay, there it is, and we're done. Okay, so that's it. It was 3 steps through the algorithm. Okay, we're going to take a look at another example. We're going to compute a much larger number. So we'll use square and multiply to compute this number here. So we're going to try to compute this 9726 to the 3533 mod 11413. Okay, so the first thing we have to do is represent 3533 in base, which is right now in base 10. We need to represent that in base 2. 3533 base 10, that is going to be 110 111 00 1101 base 2. Okay, so we now have the binary digits here of C, and then this is going to be C0, this here will be C1, etc., etc., and then this will be here C10, and then finally this one here will be C11. Okay, so that's how I'm going to refer to them in the algorithm. The algorithm will start, and we'll start with I is equal to 11. Okay, so I'm going to now draw a table. I'm not going to write it out as quite as much detail as the previous example. I'll draw a table here. I will start out something, and I'm going to have what, well, I'm going to call it here BI, but BI is well, why don't I just call it CI? Maybe that's less confusing. Call this here CI, and then I'm going to write here the calculation of Z as we're going along. So this is us going through the algorithm. So in the first step of our algorithm, I is 11, C11 is 1. And so then we would make the calculation. I mean, Z here, it starts at 1. Z starts at 1, and then we square Z. Always we square Z, and then depending if Ci is 1 or 0, we decide whether we should multiply by X or not. So in this case, X is equal to 9726. So we square Z. There it is, Z squared. And then Ci is 1, so we multiply by X, 9726. And then our result over here, our result here is 9726. Okay, we decrement I. We get 10. We look at C10. C10 is 1. So we always square Z, so we go ahead and do that. We square Z, which is now 9726. We square that, and then we multiply by X because this is a 1. Because Ci, in this case C10, is 1. So then that we multiply here 9726, and then we must now mod 1143. So I'm going to make this calculation mod 11413, and we get 2659. We decrement. We find out that C9, that's this guy right here, C9 is 0. So at this step, all we do is square Z. 2659 squared, and then that gets us here 5634. Go to the next step. CI is 1, C8 is 1. So just keep some coherence here. We square Z, and Z is currently sitting at 5, 6, 3, 4. We square that, and then we multiply by X because this number is a 1. 9726. We mod 11413, and we get 9167. Okay. And keep going. We're going to keep going. 7. What is C7? C7 is a 1. We square our current value of Z, which is that thing there. And since it's a 1, we multiply by X. We get this number here, 4958. Okay, then we decrement 6. C6 is still a 1, so we do the same thing. 4958. We square that, and then we multiply by 9726, and we get 7783. Going down to 5. C5 is 0, so the only thing we do is square Z. Done. And then we get here 6298. Okay. And then we go down 4. C4 is 0, so we do the same thing. We just simply square our current value of Z, which is 6298. We square that, and we get 4629. Coming down to C3. C3 is 1, so we square Z, 4629, and we multiply by X. And we get 10185. Next step, 2. We get that we look and we see that C2 is 1. So we square Z, and we multiply. This is what's called the square and multiply algorithm. And we're basically deciding, do we multiply or not based on the value of CI. And then that number is 105. And we just keep going here. We're almost done. We get down here 1, and C1 is 0. So we square 105, and we don't multiply by X. And we get here 11025. And then we look at C0. C0 is a 1, so we square and multiply. So we take that number 11025, we square that, and then we multiply by X. 9726, giving us 5761. Okay, so there we have the result right there. So what I'm saying is, if I was looking at this from, let me just write what this is. This is 9726 raised to the power of 3533 mod 11413, and that is equal to 5761. So if I had this number here being, this number is n in the RSA encryption, p times q. This number here is b. So this would be, and then I can be thinking of it this way: plain text equal to 9726, ciphertext is 5761. Okay, so that is the way to keep the operation count for doing this to O of L times K squared, which is bounded above by O of log N cubed. So that is the computational complexity for encryption. Okay, so that is an important implementation detail of RSA. The next thing we're going to do in the next video, I'm not going to do this here in the next video, what we're going to do is talk about how we could find large random primes. Thank you.